Up to this, you know about the character table, reducible and irreducible representations, their characters, and categorization of functions based on their transformation. Let's summarize what we have learned so far. We have a molecule, and it has a particular symmetry. For the molecular symmetry, the point group is fixed, which is, let's say, C2V. For a particular point group, the operations are also fixed. For C2V, the operations are E, C2, and to sigma V. Now, for the point group, the character table is also fixed, which contains all the irreducible representations with their characters. In C2V, we have A1, A2, B1, and B2 as the irreducible representations. Now, within this framework, we will have to consider our bases, or functions, such as coordinates and orbitals. And we will categorize them among the irreducible representations based on their transformations under the symmetry elements. Moreover, the position of some functions are also fixed within a point group and belong to particular irreducible representations. For example, z-axis will always transform as a 1 in C2V. X will always transform as B1 and Y will always transform as B2. But if we have a new molecule, then we might have certain new functions or orbitals which behavior may or may not be known to us. In that case, you must determine how they transform under each symmetry operations. Then match their transformation behavior with the character table of the point group and put them under a particular irreducible representation. While solving real problems, we do not need to apply the symmetry operations to each of the function and then find how they transform. This will demand a lot of time. For learning purposes, this is necessary. But with real molecules, we can calculate the reducible representation of the set of functions that we want to evaluate. Then we can reduce it using the reduction formulae to get the irreducible representations that are applicable for this set of functions. This can be represented as, for example, tau is equal to tau 1 plus tau 2 plus tau 3 plus tau 4. This set of reducible and irreducible representations are fixed for a particular set of functions. Let's say a point group has 4 irreducible representations, and we have to find out which irreducible representations are responsible for a set of functions, let's say x, y, and z. Here, tau is the reducible representation. When we reduce it, it will have tau 1, tau 3, and tau 4 in it. We can say tau is the superset which contains these 3 irreducible representations for x, y, and z. Next, if I change the function, then the entire set will change. For a new function, a, b, and c, the reducible representation is tau prime, and it may contain different combination of irreducible representations such as tau 1, tau 2, and tau 4. Depending on the nature of the functions, tau prime can contain 2 tau 1 and 1 tau 3. So, in group theory, the addition of representations indicates their presence in the reducible representation.